Hello, everyone. Well, I'm Alp. I know some of you because of the keyword space, but not all of you, because, well, I'm a newbie in RISC-V. So I would like to just put some context for us. We are European, so I emphasize a little bit because I have to do it while it still means something. We are also French. Okay, so that's why I just put a presentation, just a context, the space challenges in space from last week's presentation in ESCON in Spain. So I have many questions around these challenges. Of course, we won't answer now. Just I wanted to put everything in one slide. Some of you earlier this morning talked about sovereignty as well. So I think it's very important, and I know that in this room there are many of you, you already know that open source might be a good solution for this. In terms of competitiveness, this is very tough. We are behind in some ways in Europe, unfortunately. So we have to get rid of this technical debt and just push forward. The ecosystem is very important, very important. And again, when we talk about open source, the ecosystem becomes much more easier. But there is a trap, of course, because open source can be something everyone do their things on their own because they can. So this is just might be a trap as well that we need to think about. And the space specificities, of course, because now we know that space is the new black. It's very fun thing to do. Like we all know, they are in the press. Everyone talks about space as well. So these are questions that we should answer. So who are we? We are a French-based company. We have 3 offices: Paris, Montpellier, and Grenoble. Actually, we are doing FPGAs. This is a little bit weird. Well, in the space market, people know about us, but not in the other markets. When we talk about FPGAs, when I say, yeah, I work on FPGAs, I do FPGAs, they're saying, you use AMD or microchip? Which one? No, we do FPGAs. And we have currently 3 different offerings. So we do the SOC FPGAs. We offer design services. We acquired Dolphin Design last year. And we offer also silicon, different IPs. Of course, it's ITAR free because it's European, like I said, and we are mostly focused on space and defense. So this is an example of what we do. We do SOC FPGAs. Well, in the SOC, there's an ARM, but just ignore that. Okay, so it's just I don't want to get murdered this night. So we our specialty basically it's a FPGA. So we already we have a flight heritage with other models. We have started also to deliver flight models of the NG Ultra. So DUROC. DUROC is the name of the metro station in Paris, and also a project which is very ambitious. This is from the website of DUROC. It's a European project. Well, the title talks about the ultra group programmable SOC, and we are designing or thinking about this next generation Ultra 7. So this was the beginning. Of course, this will be in 7 nanometer. And we are currently working on a library. I will explain a little bit later. And we have multiple partners. I put FrontGrade in the middle because it's a very, very great partner. So in this presentation, I will focus especially on the demonstrator side and what we do in terms of radiation hardening, because this is our specialty, in fact. Why I was talking about space, because we do radiation hardened space FPGAs. This is important. Well, there was also a presentation, very interesting presentation, radiation hardening by design. Well, we do something similar. So here is the demonstrator. You already know, I think, the GPP element. I'm not, again, expert on RISC-V, but we are working with Geisler on this. So Geisler will have, the FrontGrade Geisler will have this demonstrator in N7. This will be the first time, I guess, if I'm not mistaken. We have put some radiation constraints on it. So we basically took the NG Ultra data sheet, and we are trying to do more or less the same thing, which is very good, by the way. So we are hoping to have these samples end of this year. So basically the idea is to do this demonstrator and put on radiation testing. This is very important. So first, in order to do that, we develop radiation hardened standard cells. We have this knowledge because when we do develop our FPGAs, the FPGA fabric itself, it's a custom cells, based on custom cells. So we are developing our own radiation hardened cells. Of course, in the standard cell part, the SOC part, we used for NG Ultra, for example, the 28 nanometer standard cell library. This was already hardened. Now we are doing the same thing for the 7 nanometer. So the success criteria for us, it's very important. For now, we are doing best we can, but we target the immunity. Well, immunity for the mission profiles that we are targeting, of course, because immunity is a, well, it's relative. So this is the first result, just by simulating. We use TFIT simulator. So currently, results are very promising. Of course, there is an overhead on the area side, you can see, but an area of a flip-flop, it's currently just a small contribution on the overall chip size, especially for design nodes like N7. In terms of performance, we also have very small overhead because if you take a look at the one critical path, the DFF contribution is very, very low. So this is very important. What's next? What's next? In fact, we have different projects around this ecosystem, around this platform that we need to find a fancy name. When I say European Space Ready N7 design platform, so we need to find a name. But the idea is to have to offer this platform to everyone in order, well, the radiation hardened flip-flops, design services, different IPs, either IPs or chiplets. This is another topic, but we are currently working with different institutes like ESA, CNES, and European Commission on this. So these are the projects, A12 projects from CNES. We have PUMA from European Commission, DUROC as well, and others to come. So the idea is, okay, it's ambitious, but the idea is to have this platform to build solid radiation hardened circuits in 7 nanometers.